Close your eyes and feel the gentle rhythm inside your chest. Your heart beats steadily, like a soft drum keeping time for your entire body. Each beat marks another moment passing. Each pulse moves you forward through the invisible river we call time. Right now, as you lie here in the darkness, time feels perfectly normal. It flows around you like a calm stream, carrying you from this breath to the next. 1 second follows another in perfect order. Minutes stack into hours. Hours build into days. This is the time you know. This is the time that feels real. But what you feel is only part of the story. Your body is a collection of clocks, all ticking together in harmony. Your heart beats roughly once every second. Your lungs fill and empty in a gentle rhythm. Deep inside your cells, tiny molecular machines spin and turn, keeping the chemistry of life moving forward. Even your brain waves pulse in patterns, like ocean swells rolling toward shore. All these rhythms feel connected to something larger. Something we call time itself. You wake up when morning light touches your window. You feel hungry when your internal clock says it's time to eat. You grow sleepy when darkness falls, as if your body knows exactly where it sits in the flow of time. For thousands of years, humans believed time was like a giant river flowing in one direction. Everyone everywhere moved through this river at exactly the same speed. A minute for you was a minute for someone on the other side of the world. A year on Earth was a year everywhere in the universe. Time seemed fixed, unchanging, as solid as the ground beneath your feet. But time holds secrets. Imagine you could step outside your body and watch yourself from above. You would see your chest rising and falling. You would see your heart pushing blood through your veins. You would see all the tiny motions that keep you alive. But you would also see something invisible. You would see time itself moving through you, shaping every process in your body. Time doesn't just carry you forward. It participates in everything you are. The oxygen in your lungs takes time to reach your blood. Your thoughts take time to travel along your nerves. Even light takes time to travel from your lamp to your eyes, though that time is almost too small to imagine. Your body experiences time in layers. Your heartbeat marks seconds. Your breathing counts longer moments. Your sleep cycle measures the rhythm of days. But beneath all these familiar rhythms, something stranger is happening. Time itself is more flexible than you might think. Right now, time moves differently in different parts of your body. The time flowing past your feet is slightly different from the time flowing past your head. The difference is incredibly small. So small that your body can't feel it. But it's real. It's always been real. Scientists can measure it with the most sensitive clocks ever built. This tiny difference exists because time responds to gravity. The Earth pulls on your body, and that pull affects how time flows. Near the ground, where gravity is strongest, time moves just a little slower. Higher up, where gravity is slightly weaker, time moves just a little faster. Your head lives in a slightly faster time than your feet. The difference is smaller than a whisper. Smaller than a thought. In your entire lifetime, your head will age only a few billionths of a second more than your feet. But this tiny difference points to something amazing. Time is not the solid, unchanging river we once believed it to be. Time can stretch. Time can compress. Time can flow at different speeds in different places. What feels perfectly steady to you is actually flexible, responsive, alive with possibility. Think about water for a moment. Water seems simple when it sits calmly in a glass. But water can become ice when it gets cold enough. Water can become steam when it gets hot enough. Water can flow fast in a narrow stream or spread slowly across a wide lake. Water changes its behavior depending on what happens around it. Time is like water in ways we're only beginning to understand. When you move very fast, time slows down around you. When you're near something very heavy, time pulls and thickens. When you accelerate, time bends and curves. These effects are usually too small to notice in everyday life. But they're always there, quietly shaping the universe around you. Scientists have sent atomic clocks on airplanes and watched time slow down. They've placed identical clocks at different heights and measured how time flows differently at each level. They've tracked particles moving at incredible speeds and seen time stretch like taffy around them. What seems impossible is actually happening all around you, all the time. Your experience of time, steady, predictable, flowing in one direction, is like standing in a calm part of a vast ocean. The water around you feels still and peaceful. But beneath the surface, powerful currents flow in complex patterns. Waves travel in every direction. The ocean is alive with motion you can't see from where you stand. Tonight, you're about to dive beneath the surface of time itself. You're going to explore the hidden currents and secret depths that most people never see. You're going to discover how motion changes time, how gravity bends it, and how the universe uses these invisible forces to create the reality around you. But you won't leave the safety of this quiet moment. You'll carry this calm feeling with you as you journey into the strange and beautiful mathematics of Einstein's universe. You'll learn to see time as it really is, not a river, but an ocean full of wonders. As you settle deeper into rest, feel your heartbeat marking time in the most personal way possible. Soon, you'll discover how that same heartbeat would tick differently if you were moving through space at incredible speeds, or standing near a star, or floating in the gentle curve of space-time itself. Picture a young man with wild, curly hair sitting by a train station window. The year is 1905. Outside, steam engines chug past, carrying passengers to distant cities. Inside, Albert Einstein watches and wonders. His mind is always asking questions that others never think to ask. What if you could run as fast as light itself? What would the world look like? What would happen to time? These gentle questions seem simple, almost childlike. But they will change everything we know about the universe. Einstein doesn't work in a fancy laboratory. He works at a patent office, examining other people's inventions all day long. Clocks, machinery, devices for measuring time and space. But in his spare moments, his mind wanders to bigger mysteries. He imagines riding alongside a beam of light, like running next to a train to see what it looks like from the side. Most scientists in 1905 believe that space and time are completely separate things. Space is the stage where everything happens. Time is the clock that measures when things happen. They seem as different as water and air. Everyone knows that if you want to meet a friend, you need to agree on both where and when. The where is space. The when is time. Simple. But Einstein's imagination sees deeper connections. He realizes that light behaves strangely. No matter how fast you move toward a beam of light, or away from it, the light always passes you at exactly the same speed. This seems impossible. If you run toward a friend who's walking toward you, you meet each other faster. If you run away from that friend, it takes longer to meet. Everything in everyday life works this way. Everything except light. Light always moves at the same speed relative to you, no matter how you move. Einstein sits quietly, thinking about what this means. His mind works like a patient gardener, turning over the soil of old ideas to see what might grow underneath. If light always travels at the same speed for everyone, then something else must change when you move very fast. But what? The answer comes to him like dawn breaking over a calm lake. Time itself must change. When you move very fast through space, you move more slowly through time. When you slow down in space, you speed up in time. Space and time are not separate things at all. They're woven together like threads in a single fabric. Einstein calls this fabric space-time. This idea feels impossible at first. Time seems so solid, so unchanging. Every clock in every house ticks at the same rate. Every heartbeat marks the same length of moment. But Einstein realizes that our everyday experience only shows us a tiny corner of a much larger reality. Imagine you're standing in a shallow part of the ocean. The water around your ankles feels calm and still. You might think the entire ocean is just like this quiet spot. But step deeper and you discover currents you never knew existed. Waves that rise and fall in complex patterns. Temperatures that change with depth. The ocean near shore is just the beginning of something vast and mysterious. Time is like that ocean. Your everyday experience shows you only the shallow, calm parts. But deeper in the ocean of space-time, incredible things are happening. Einstein works out the mathematics slowly, carefully. He discovers that time dilates, stretches like warm honey when you move fast or when you're near heavy objects. He finds that space contracts, shrinks like a deflating balloon when you accelerate to high speeds. He realizes that what we call now depends on where you are and how you're moving. None of this matches our everyday experience. But Einstein trusts the mathematics more than common sense. The equations point toward a universe far stranger and more beautiful than anyone imagined. His work doesn't happen in a flash of inspiration. It grows slowly, like a tree adding rings year by year. He thinks about moving trains and flashing lightning. He imagines elevators falling through space and clocks ticking at different rates. Each thought experiment adds another piece to the puzzle. Einstein discovers that massive objects bend space-time like a heavy ball pressing down on a stretched rubber sheet. This bending of space-time is what we experience as gravity. The Earth doesn't pull you down with some mysterious force. Instead, the Earth curves the space and time around you, and you follow that curve like a marble rolling along a slope. The young man by the train station window has unlocked secrets that were hidden since the beginning of time. But he does it gently, with curiosity instead of force. With imagination instead of complicated equipment. With questions instead of answers. His discoveries seem abstract at first. Who cares if time runs slightly differently for someone moving very fast? Who cares if clocks tick at different rates in different places? These effects are far too small to notice in everyday life. But Einstein's gentle revolution touches everything. Every satellite circling overhead must account for time running differently at their altitude. Every GPS system in every phone uses Einstein's equations to tell you where you are. Every particle accelerator, every nuclear power plant, every star burning in the night sky operates according to the rules Einstein discovered while watching trains. The universe is not the simple, predictable place it seemed to be before 1905. It's a place where time can stretch and compress. Where space can bend and curve. Where the past, present, and future might not be as separate as they seem. As you rest here in the darkness, Einstein's discoveries quietly shape the world around you. The time flowing through your body follows laws that seemed impossible just over a century ago. Your very existence depends on the strange, beautiful rules of spacetime that a young man figured out by asking simple questions about light. Tonight, you'll follow the path Einstein opened. You'll discover how motion changes the flow of time itself, starting with something as basic as the speed of light. Right now, light is touching your face. Even in this darkness, invisible particles of light are finding their way to you. Some bounce off the walls. Some leak through curtains. Some come from the gentle glow of electronic devices. Each tiny packet of light, each photon, has traveled to reach you at exactly the same speed. This speed is not just fast. It is the speed that defines everything else in the universe. Light travels at 186,282 miles per second. This number seems impossible to imagine. In 1 second, light could circle the entire Earth more than 7 times. In the time it takes you to blink, light could travel from New York to Los Angeles and back again. In the time it takes to say the word "a light," a photon could journey to the moon. But the true mystery isn't how fast light moves. The mystery is that light always moves at exactly this speed, no matter what. Imagine you're standing beside a road, watching cars drive past. If a car is moving toward you at 60 miles per hour, and you start walking toward that car at 3 miles per hour, the car approaches you at 63 miles per hour. The speeds add together. This makes perfect sense. This is how everything in your everyday world behaves. Everything except light. If you run toward a flashlight beam at any speed, the light still approaches you at exactly 186,282 miles per second. If you run away from that same beam, it still catches up to you at exactly 186,282 miles per second. The light doesn't care how fast you're moving. It maintains its own perfect, unchanging pace. This strange behavior puzzled scientists for decades. They tried to explain it by imagining that light moves through an invisible substance, like waves moving through water. They called this imaginary substance the ether. They thought the ether filled all of space, giving light something to move through. But every experiment designed to detect the ether failed. Space appeared to be truly empty. Light somehow moves at constant speed through absolute nothingness. This seemed impossible, like a fish swimming through air, or a bird flying through solid rock. Einstein realized that everyone was asking the wrong question. Instead of asking what light moves through, he asked what it means for light to always move at the same speed. The answer changed everything. The speed of light isn't just the speed that light happens to travel. It's the speed limit of the universe itself. It's the maximum speed that anything can move through space. It's the speed that connects space and time into a single, unified fabric. Think of space-time as a vast landscape with its own natural speed limit. Just as every highway has a maximum safe speed, space-time has a cosmic speed limit. That limit is the speed of light. Nothing with mass can ever reach this speed. Nothing can ever exceed it. Light reaches this ultimate speed because light has no mass at all. Photons are pure energy, weightless packets of electromagnetic force. They don't have to accelerate up to light speed. They exist at light speed. From the moment they're created until the moment they're absorbed, they move at exactly 186,282 miles per second. This cosmic speed limit shapes everything that happens in the universe. When you try to make something move faster and faster, it becomes harder and harder to speed it up more. The closer you get to light speed, the more energy you need to go even a little faster. To actually reach light speed would require infinite energy, which is impossible. But here's where the story becomes truly beautiful. As you approach the speed of light, time itself begins to slow down around you. Space begins to contract in the direction you're moving. The universe literally reshapes itself to maintain the cosmic speed limit. Every photon that has ever touched your skin carries stories from across the universe. The light from your bedroom lamp traveled almost instantly from the bulb to your eyes. But the light streaming through your window might have left the sun 8 minutes ago. The light from the nearest star beyond our sun started its journey over 4 years ago. Some of the photons reaching your eyes tonight began their travels when dinosaurs walked the Earth. Others started their journey before Earth even existed. Each particle of light is a messenger from a distant place and time, all arriving at your eyes at exactly the same speed. The light from distant galaxies has been traveling for billions of years to reach you. When you look up at the night sky, you're seeing light that left those stars when the universe was young. You're looking backward through time, watching the ancient history of the cosmos unfold. But every photon, whether it traveled for microseconds or billions of years, arrives at your eyes moving at exactly the same speed. Time and distance don't matter to light. It simply moves, constant and sure, carrying information across the vast emptiness of space. This constancy of light speed creates a kind of cosmic democracy. No matter where you are, no matter how you're moving, light always approaches you at the same speed. It doesn't matter if you're sitting still on Earth or flying through space in a rocket ship. Light treats everyone the same. The speed of light is woven into the very structure of reality. It appears in equations that describe electricity and magnetism. It shows up in formulas that govern nuclear reactions. It connects energy and mass in Einstein's famous equation, E equals mc squared. The c in that equation stands for the speed of light. Every time you use electricity, you're depending on the speed of light. The electromagnetic fields that carry power through wires move at light speed. Every time you look in a mirror, you're seeing light that bounced off the surface and traveled to your eyes at exactly 186,282 miles per second. This speed is not just a measurement. It's a fundamental property of the universe, as basic as the existence of space and time themselves. It's the speed at which cause and effect propagate through reality. It's the speed at which change spreads from one place to another. As you rest here in the gentle darkness, remember that you're surrounded by light moving at this cosmic speed. Even the heat radiating from your body is a form of light, infrared light that your eyes can't see, but that carries energy at the same fundamental speed as all other light. The constancy of this speed creates the framework within which time can stretch and bend. When you move very fast, time slows down precisely because the speed of light must remain constant. The universe reshapes time itself to preserve this sacred speed. Feel your heartbeat right now. Steady. Rhythmic. Marking time like a gentle drum in your chest. Each beat takes roughly 1 second. This is your personal clock, keeping perfect time as you lie still in the darkness. But what if you could somehow take your heartbeat on a journey at incredible speeds? What if you could travel so fast that your heart itself became part of an experiment in time? Your heart would still beat at exactly the same rhythm it always has. From your perspective, nothing would change. 1 beat, 1 second. 1 beat, 1 second. Your personal time would feel completely normal. But something extraordinary would be happening around you. Time itself would be slowing down. This isn't science fiction. This is one of the most beautiful and strange truths Einstein discovered about our universe. When you move very fast through space, you move more slowly through time. The faster you go, the more dramatically time stretches and extends around you. Think of motion and time as partners in a cosmic dance. They're always connected, always balancing each other. When one increases, the other must decrease. It's as if the universe has a fixed amount of motion to distribute, and it must choose how to divide that motion between moving through space and moving through time. Right now, as you rest completely still, you're moving through time at maximum speed. Every second that passes for you is a full second. Every minute is a complete minute. You're traveling through time as fast as anyone can travel when they're not moving through space at all. But imagine you could somehow accelerate to enormous speeds. As you begin to move faster and faster through space, something remarkable happens to your journey through time. It begins to slow down. The effect is tiny at first. Walking speed, running speed, even driving in the fastest car, these everyday motions barely affect time at all. The changes are so small that the most sensitive clocks can barely detect them. But the effect is always there, quietly working in the background of reality. Scientists have measured this effect using atomic clocks, the most precise timekeepers ever built. They've put identical clocks on airplanes and watched them fall slightly behind clocks that stayed on the ground. The flying clocks experienced less time because they were moving faster through space. The faster you move, the more dramatic the effect becomes. At the speed of a commercial jet, you might lose a few billionths of a second during a long flight. At the speed of a rocket leaving Earth, you might lose microseconds. But as you approach the speed of light, time begins to stretch like warm honey. Imagine traveling at 90% the speed of light. From your perspective, inside your high-speed ship, everything feels normal. Your heartbeat keeps its steady rhythm. Your thoughts move at their usual pace. Your personal clocks tick normally. But relative to someone watching from Earth, your time has slowed dramatically. What feels like 1 hour to you becomes more than 2 hours for the person watching from Earth. Your heart, beating normally from your perspective, appears to beat much more slowly to outside observers. Your movements seem to happen in slow motion. Even light inside your ship appears to move normally to you, but seems sluggish to anyone watching from the outside. This time stretching isn't an illusion or a trick of measurement. It's a fundamental feature of reality. Time really does slow down when you move fast. The effect is completely real and measurable. The mathematics behind this effect is elegant and simple. As your speed increases toward the speed of light, time dilation becomes more and more extreme. At 99% the speed of light, time slows by a factor of 7. At 99.9%, it slows by a factor of 22. At 99.99%, time crawls by at nearly 70 times slower than normal. But here's the truly mind-bending part: this effect is completely symmetrical. If you're moving fast relative to someone else, they appear to be moving fast relative to you. From your perspective, their clocks would seem to be running slow. From their perspective, your clocks would seem to be running slow. Each observer sees the other's time as dilated. This seems like a contradiction, but it's not. The apparent contradiction only matters when you try to bring the two observers back together to compare their experiences. And that's when things get even more interesting, involving acceleration and the deeper mysteries of curved space-time. The universe appears to have a conservation law for motion itself. You can move quickly through space, or you can move quickly through time, but you cannot do both at maximum speed simultaneously. The total amount of motion through space-time remains constant. It's simply distributed differently between space and time depending on how fast you're traveling. Think of this like a river flowing at a constant rate. If the river widens, the water moves more slowly. If the river narrows, the water moves more quickly. The total flow remains the same, but it's distributed differently across the available space. In spacetime, your total motion is always at the speed of light. When you're sitting still in space, all of that motion goes into moving through time. When you're moving fast through space, some of that motion gets redirected away from time and into spatial movement. The total motion remains constant, but its distribution changes. This redistribution of motion explains why nothing with mass can ever reach the speed of light. At light speed, all of your motion would be through space, leaving none for movement through time. Time would stop completely. This is a physical impossibility for anything that has mass. Only light itself, which has no mass, can travel at the speed of light. For light, all motion is through space and none through time. From a photon's perspective, if it could have a perspective, no time passes during its journey. A photon travels from the surface of the sun to your eye instantaneously, from its own point of view. As you rest here in the gentle stillness, your motion is entirely through time. Each second passes at its fullest, richest pace. You're experiencing time at its most concentrated, undiluted by the demands of rapid spatial motion. But even this stillness is relative. Earth spins on its axis and orbits the sun. The sun moves through the galaxy. The galaxy moves through space. All of these motions create tiny, subtle effects on the flow of time around you. Soon, you'll discover how massive objects like planets and stars create their own distortions in the flow of time, bending and pulling it like gravity bends space itself. Right now, as you lie still in the darkness, gravity is holding you gently against the Earth. You feel its steady pull as weight, as the comfortable pressure of your body settling into your bed. But gravity is doing something else, something far more mysterious. It's quietly changing the flow of time around you. Your feet, pressed closer to the Earth's center, experience time slightly differently than your head. The difference is impossibly small, smaller than a single heartbeat in a lifetime. But it's real. It's measurable. And it reveals one of the universe's most beautiful secrets. Gravity doesn't just pull objects toward each other. It bends the fabric of spacetime itself. Imagine spacetime as a vast, stretched sheet of soft rubber. When you place a heavy ball in the center of this sheet, it creates a depression, a curved valley where the rubber bends downward. Smaller objects placed near the heavy ball naturally roll toward it, following the curved shape of the sheet. This is how gravity works, but instead of a rubber sheet, the sheet is the four-dimensional fabric of space and time woven together. Massive objects like Earth create curves and valleys in this fabric. You don't fall toward Earth because of some mysterious pulling force. You follow the curved path that Earth's mass has created in spacetime itself. But here's where the story becomes truly magical. Time flows differently in different parts of these curved valleys. Deep in a gravitational well, where spacetime is curved most dramatically, time moves more slowly. Higher up, where spacetime is flatter and less curved, time moves more quickly. The difference is subtle in everyday situations, but it's always there, like a quiet song that only the most sensitive instruments can hear. Your feet rest about 6 feet closer to Earth's center than your head. In those 6 feet, gravity is slightly stronger. The curvature of space-time is slightly more pronounced. And time, responding to this curvature, flows just a tiny bit more slowly. Over the course of your entire lifetime, your feet will age about 90 billionths of a second less than your head. This difference is far too small for your body to notice. But atomic clocks can detect it easily. Scientists have measured this effect by placing identical clocks at different heights and watching them slowly drift apart. The taller the building, the greater the difference. A clock on the ground floor of a skyscraper will tick slightly slower than an identical clock on the top floor. The difference amounts to only a few nanoseconds per day, but it accumulates over time. GPS satellites orbiting high above Earth must account for this effect to maintain their accuracy. The closer you get to a massive object, the more dramatically time slows down. On the surface of the Sun, time moves about 66 seconds slower per year compared to time far from any star. Near a neutron star, where gravity is incredibly strong, time might slow by significant fractions. Near a black hole, time can slow to almost nothing at all. This time dilation happens because massive objects literally warp the geometry of space-time. Einstein realized that what we experience as gravity is actually the result of moving through curved space-time, like a marble rolling along the slopes and valleys of a landscape shaped by mass and energy. Think of time as water flowing down a mountainside. In flat areas, the water moves quickly and smoothly. In valleys and depressions, the water pools and flows more slowly. Near massive objects, space-time creates deep valleys where time pools and thickens like honey on a cold morning. This effect connects motion and gravity in surprising ways. Einstein discovered that acceleration feels exactly like gravity. If you're in an elevator accelerating upward, you can't tell the difference between that acceleration and the pull of gravity. This insight led him to understand that gravity and acceleration are different faces of the same phenomenon. When you accelerate quickly in a car, you feel pressed back into your seat. When you stand on Earth's surface, you feel pressed down by gravity. These sensations feel identical because they are identical. Both involve moving through curved space-time, just in different ways. The curvature of space-time also explains why gravity affects everything equally. A feather and a hammer dropped on the moon fall at exactly the same rate, despite their different masses. This happens because both objects are simply following the same curved path through space-time. The path is determined by the moon's mass, not by the mass of the falling objects. This universality of gravitational effects extends to time itself. All clocks, mechanical, electronic, biological, atomic, slow down equally in strong gravitational fields. Your heartbeat, your thoughts, the vibrations of atoms in your body, all experience the same time dilation. From your perspective, time always feels normal, no matter how strong the gravity around you. But compared to someone in a weaker gravitational field, your entire existence would appear to be running in slow motion. Your speech would sound deeper and slower. Your movements would appear more deliberate. Even light leaving your location would appear redder to distant observers, stretched by the gravitational field it climbs out of. The Sun's gravity creates a gentle valley in spacetime that extends far beyond Earth's orbit. Earth rolls around this valley like a marble circling the bottom of a bowl. But Earth also creates its own smaller valley, and the Moon rolls around Earth's gravitational depression. These nested valleys of curved spacetime create the elegant dance of orbital motion. Every massive object in the universe contributes to the overall curvature of spacetime. Stars, planets, galaxies, even you, all bend spacetime according to their mass and energy. The result is a vast, dynamic landscape of curves and slopes, valleys and hills, all invisible to your eyes but felt by everything that moves through space and time. As you rest here, Earth's mass is creating a gentle depression in spacetime around you. You're not being pulled downward by a mysterious force. You're simply following the natural curvature of spacetime, like a ball rolling along a tilted surface. Your experience of weight is actually the sensation of being pressed upward by your bed, preventing you from following spacetime's natural curve. The atoms in your body, the air around you, the light from your lamp, everything participates in this cosmic geometry. Space-time curves smoothly around Earth's mass, creating the comfortable, familiar sensation of gravity that has shaped life on this planet for billions of years. Tonight, as you drift towards sleep, you're cradled not just by your bed, but by the curved fabric of space-time itself. The same curvature that keeps Earth orbiting the Sun and the Moon orbiting Earth also holds you gently in place, while time flows at its own quiet pace around you. Soon, you'll journey beyond Earth's gentle gravitational embrace to discover what happens when time dilation becomes so extreme that it transforms the very nature of existence itself. Imagine an astronaut preparing for a long journey to the International Space Station. Her name is Sarah, and she's about to become a time traveler without leaving our solar system. She doesn't know it yet, but when she returns to Earth 6 months later, she will have aged slightly less than everyone who stayed behind. Sarah straps herself into the rocket, feeling the familiar weight of gravity pressing her into her seat. Her heart beats steadily as the countdown reaches 0. The engines ignite with tremendous force, pushing her upward at incredible speeds. As the rocket accelerates away from Earth, something remarkable begins to happen to time itself. The faster Sarah travels, the more time slows down around her. During the violent acceleration phase of launch, her personal time moves just a tiny bit slower than time on Earth's surface. The effect is incredibly small, measured in microseconds, but it's real and measurable. Once Sarah reaches the space station, she experiences time dilation in 2 different ways. First, she's moving very fast relative to Earth, orbiting our planet at about 17,500 miles per hour. This high speed causes her time to slow down compared to people on the ground. But there's a second effect working in the opposite direction. The space station orbits about 250 miles above Earth's surface. At this altitude, gravity is weaker than it is on the ground. Remember how time flows more slowly in stronger gravitational fields? Since Sarah is farther from Earth's center, she's in a slightly weaker gravitational field, which means her time actually moves a little faster than time on Earth's surface. These 2 effects, one from her high speed, one from the weaker gravity, work against each other. But the gravitational effect is stronger. The result is that Sarah's clocks tick slightly faster than clocks on Earth. Her biological processes, her heartbeat, her thoughts, all run just a tiny bit faster relative to Earth time. Over the course of her 6-month mission, Sarah ages about 14 milliseconds more than she would have if she had stayed on Earth. 14 thousandths of a second. Less than the blink of an eye. But this tiny difference represents something profound about the nature of time and space. Sarah doesn't feel any of these effects. From her perspective inside the space station, time flows normally. Her watch ticks at its usual pace. Her meals arrive on schedule. Her sleep cycles remain steady. The only way to detect the time difference is to compare ultra-precise atomic clocks, one on the station, one on Earth. During her months in space, Sarah looks down at Earth spinning slowly beneath her. She watches sunrises and sunsets flow past every 90 minutes as the station completes its orbit. Each orbit takes her around the entire planet in the time it would take to watch a movie. But she doesn't realize that her experience of those 90-minute periods is slightly different from the experience of people on the ground. The people Sarah left behind, her family, her friends, her colleagues, live through those same 6 months at Earth's pace. They experience the full weight of gravity, keeping them firmly planted on the surface. Their time flows at the rate determined by Earth's mass and their relatively slow motion through space. When Sarah finally returns to Earth, the difference in elapsed time is too small for human senses to detect. She doesn't feel younger. She doesn't look different. Her memories of the mission feel like exactly 6 months of experience. But according to the atomic clocks, she has lived through slightly more time than the people who stayed on Earth. This isn't science fiction or theoretical physics. This effect has been measured precisely on every long-duration space mission. Astronauts who spend months on the International Space Station really do age differently than people on Earth. The difference is tiny, but it's real and consistent with Einstein's predictions. The same principles apply to any situation involving different speeds or different gravitational fields. A person living at the top of a mountain ages slightly faster than someone living at sea level. A person flying frequently in airplanes experiences tiny amounts of time dilation. Even the simple act of walking makes time flow differently for you than for someone sitting still. These effects are usually far too small to matter in everyday life. But they become important for systems that require extreme precision. GPS satellites, for example, must account for both types of time dilation. They orbit high above Earth where gravity is weaker, causing their clocks to run fast. But they also move at high speeds, causing their clocks to run slow. Engineers must calculate both effects precisely to keep GPS systems accurate. Sarah's journey reveals something beautiful about the universe. Time is not the rigid, unchanging backdrop we once thought it was. It's flexible, responsive, intimately connected to motion and gravity. Every journey through space is also a journey through time, even if the effects are too small to notice. The mathematics that govern Sarah's time dilation are the same mathematics that govern the most extreme environments in the universe. Near neutron stars, where gravity is millions of times stronger than Earth's, time slows dramatically. Near black holes, time can nearly stop altogether. But the principles Sarah experiences in Earth orbit, the interplay between motion and gravity, the flexibility of time itself, apply everywhere. As Sarah readjusts to life on Earth, she carries with her the invisible experience of having traveled through time differently than everyone else. Her cells, her memories, her very existence bears the subtle mark of Einstein's universe, where time bends and flows according to the cosmic dance of matter and energy. Her journey reminds us that we're all time travelers, constantly moving through the four-dimensional landscape of space-time. Every step we take, every mile we drive, every flight we board changes our passage through time in tiny, measurable ways. Tonight, as you rest motionless in your bed, you're taking the most direct path through time possible. But soon you'll discover how the technologies around you depend on understanding time's flexible nature. Right now, as you rest in the darkness, 24 satellites are silently circling the Earth above you. They move in careful patterns across the sky, each one carrying the most precise clocks humans have ever built. These metal guardians are performing a quiet miracle that touches your life every day, though you rarely think about them. They're using Einstein's discoveries about time to help you find your way in the world. Each GPS satellite orbits Earth twice a day, following paths that carry them 12,500 miles above your head. From that great height, they can see vast stretches of the planet's surface. They broadcast gentle radio signals that carry a simple message, their exact location and the precise time according to their onboard atomic clocks. Your phone listens to these signals whenever you use a map or ask for directions. By measuring how long the radio waves take to travel from each satellite to your device, your phone can calculate exactly where you are on Earth's surface. The mathematics is elegant and simple. But it only works because scientists understand how time behaves differently in space. Up there in their high orbits, the GPS satellites experience time dilation in two ways, just like the astronauts you learned about earlier. They're moving fast relative to Earth's surface, which makes their time slow down slightly. But they're also much farther from Earth's center, where gravity is weaker, which makes their time speed up. The gravitational effect is stronger than the motion effect. The result is that clocks on GPS satellites tick about 38 microseconds faster each day than identical clocks on Earth's surface. 38 millionths of a second per day. It seems impossibly small, but it would quickly destroy the system's accuracy if engineers didn't account for it. Think about what this tiny time difference means for finding your location. GPS works by measuring the time it takes radio signals to travel from satellites to your phone. These signals move at the speed of light, 186,282 miles per second. Even a tiny error in timing creates a large error in distance measurement. If the satellite clocks ran 38 microseconds fast each day, and engineers didn't correct for this, your GPS would think you were about 7 miles farther from each satellite than you actually are. After just one day, your phone would place you in the wrong location by several miles. After a week, the error would be enormous. The system would be completely useless. But engineers do correct for this effect. Before the GPS satellites were launched, scientists calculated exactly how much time dilation each satellite would experience in its orbit. They programmed the satellite clocks to tick slightly slower than Earth time, knowing that relativity would speed them up to the correct rate once they reached their orbits. It's a beautiful example of using Einstein's discoveries to solve practical problems. The satellite's atomic clocks are deliberately programmed to be wrong on Earth, so they'll be exactly right in space. Time dilation transforms an intentional error into perfect accuracy. Every time you use your phone to navigate, you're depending on these relativistic corrections. When you ask for directions to a restaurant, your phone receives signals from at least 4 satellites. It measures the travel time of each signal with incredible precision, then uses those measurements to calculate your exact position on Earth. The calculations happen almost instantly, billions of times around the world every day. Farmers use GPS to guide their tractors across fields. Ships use it to navigate across oceans. Airplanes use it to land safely in fog. Emergency responders use it to find people who need help. All of these applications depend on understanding how time flows differently in space. The GPS system represents one of the most practical applications of Einstein's theories. But it's also a daily reminder of how strange and beautiful the universe really is. Every time you check your location on your phone, you're witnessing the effects of curved spacetime and time dilation, translated into useful information by clever engineering. The satellites themselves are marvels of precision. Each one carries multiple atomic clocks that are accurate to within billionths of a second. These clocks measure time by counting the vibrations of cesium atoms, which oscillate at a precise frequency that never changes. The satellites compare their multiple clocks constantly, ensuring that their time signals remain perfectly accurate. Solar panels spread like metallic wings from each satellite, capturing sunlight to power the atomic clocks and radio transmitters. The satellites are built to last for decades in the harsh environment of space, bombarded by radiation and extreme temperatures, yet maintaining their precise timekeeping throughout their operational lives. From your perspective on Earth, the GPS constellation is invisible except for the occasional glint of reflected sunlight. But the satellites are always there, always broadcasting their careful messages about location and time. They're a technological constellation, as reliable as the stars ancient sailors used for navigation, but far more precise. The system works so well that it has become invisible to most people. You pull out your phone, open a map, and see your location marked with a blue dot. It seems simple, natural, almost magical. But behind that blue dot lies some of the most sophisticated physics and engineering humans have ever achieved. The GPS satellites are constantly falling toward Earth, following curved paths through the gravitational field that surrounds our planet. But they're also moving fast enough sideways that they keep missing Earth as they fall. This creates their stable orbits, perfect circles in the sky that repeat the same patterns day after day, year after year. Each satellite knows its own orbit with incredible precision. Ground-based tracking stations monitor their positions constantly, making tiny corrections when needed. The satellites adjust their paths using small thrusters, maintaining their positions in the careful dance that keeps the entire system functioning. As you drift toward sleep tonight, those satellites continue their quiet work above you. Their atomic clocks tick steadily, their radio transmitters send out their precise signals, and their solar panels track the sun across the sky. They're performing a continuous experiment in relativity, proving Einstein's theories billions of times every day while helping people navigate the world below. Soon, you'll explore an even more dramatic thought experiment about time, one that reveals how the strange effects of relativity can create puzzles that seem impossible to solve. Imagine twins born on the same day, at the same moment. Let's call them Elena and Maya. They grow up together, sharing birthdays, sharing time, their lives flowing in perfect parallel. Their hearts beat with the same rhythm. Their cells divide at the same rate. Time carries them forward together, step by step, breath by breath. But one day, Maya decides to become an astronaut. She trains for years, preparing for humanity's first journey to a nearby star. Elena becomes a teacher, staying on Earth to educate the next generation. The twins are still synchronized, still aging together, still sharing the same flow of time. Then comes the day of departure. Maya climbs aboard a spacecraft capable of traveling at 90% the speed of light. Elena stands on the ground, watching her sister disappear into the star-filled darkness. Both twins are exactly 30 years old. Both carry identical atomic clocks. Both believe they will age at the same rate during their separation. But the universe has different plans. As Maya's spacecraft accelerates to incredible speeds, time begins to behave differently around her. From her perspective inside the ship, everything feels completely normal. Her heart beats steadily. Her thoughts flow at their usual pace. Her atomic clock ticks regularly, marking seconds, minutes, hours just as it always has. Maya looks out the window and watches Earth shrink to a pale blue dot behind her. The journey to the nearby star takes her 5 years of ship time. She spends time exploring, gathering samples, making discoveries. Then she turns around and begins the 5-year journey home. From her perspective, she's been gone for exactly 10 years when she finally returns to Earth. But Elena experiences something very different. Back on Earth, Elena watches the years pass slowly. She teaches her students about the stars, wondering about her sister traveling among them. Her atomic clock, identical to Maya's, ticks steadily through the seasons. Spring follows winter, summer follows spring. Elena ages normally, feeling each year pass in its fullness. When Maya's spacecraft finally appears in Earth's sky, Elena has lived through 23 years since her sister's departure. She's now 53 years old. Her hair shows streaks of silver. Fine lines have appeared around her eyes. She's lived through 2 decades of birthdays, holidays, and quiet moments of missing her twin. Maya steps off her spacecraft, and the twins face each other after their long separation. Maya is 40 years old. Elena is 53. 13 years of difference have opened between them like a gentle canyon carved by time itself. This isn't science fiction. This is what Einstein's equations predict would actually happen. During Maya's high-speed journey, time dilation stretched each of her seconds into longer intervals as measured from Earth. What felt like 1 second to Maya lasted more than 2 seconds for Elena. What felt like 1 year to Maya contained more than 2 years of Earth time. The effect was completely symmetrical during the straight-line portions of Maya's journey. While Maya traveled away from Earth at high speed, each twin observed the other's clocks running slow. Maya saw Elena's signals arriving slowly, indicating that Elena's time was passing slowly. Elena saw Maya's signals arriving slowly, indicating that Maya's time was passing slowly. But the symmetry broke when Maya turned around to come home. To change direction, Maya had to decelerate, stop, and accelerate back toward Earth. During this turnaround phase, she experienced powerful acceleration forces. Einstein showed that acceleration is equivalent to gravity, and gravity affects the flow of time. During Maya's turnaround, she briefly experienced the equivalent of an enormously strong gravitational field. This caused her to observe Elena's clocks suddenly speeding up dramatically. In Maya's reference frame, Elena aged rapidly during the turnaround period, making up for the slow aging Maya had observed during the outbound journey. But Elena never experienced any unusual acceleration. She remained in Earth's gentle gravitational field throughout Maya's entire journey. She never saw Maya's clock speed up to compensate. From Elena's perspective, Maya's clocks ran slow during the entire trip. The result is real and measurable. Maya returns younger than Elena by exactly the amount Einstein's equations predict. This thought experiment reveals something profound about the nature of time and motion. Time is not the universal, unchanging backdrop we once believed it to be. It's intimately connected to motion, acceleration, and gravity. Different paths through space-time lead to different amounts of aging. The twin story shows that there's no absolute standard for the passage of time. Elena's experience is just as valid as Maya's. Each twin ages normally according to their own clocks and their own reference frame. But when they reunite and compare their experiences, the difference in their ages tells the story of their different journeys through space-time. This paradox isn't really a paradox at all. It's a beautiful illustration of how motion reshapes the experience of time. The twin who accelerates, who changes reference frames, who takes the more complex path through space-time, experiences less aging than the twin who follows a simpler path. Scientists have tested versions of this effect using atomic clocks and high-speed particles. When particles are accelerated to near light speed in particle accelerators, their internal clocks slow down exactly as Einstein predicted. When atomic clocks are flown on airplanes, they age differently than clocks that stay on the ground. The twin paradox reminds us that time is deeply personal. Your passage through time depends on your motion through space. Every journey you take, every acceleration you experience, subtly changes your path through the fabric of space-time. As Maya and Elena embrace after their long separation, they carry different amounts of lived experience. Maya remembers 10 years of journey among the stars. Elena remembers 23 years of life on Earth. Both memories are real. Both experiences are valid. Time has simply treated them differently because they chose different paths through the universe. The twins' reunion is both joyful and bittersweet. They've been given different amounts of time to live their lives, but they're still sisters, still connected by love and shared history. The universe has written different stories in their cells, but those stories are part of the same larger tale about the flexibility of time itself. Tonight, as you rest in your bed, you're taking the most direct path through time possible. But the universe holds spaces where time moves so slowly that a single moment might stretch toward eternity. Deep in space, where stars have lived and died, something extraordinary waits in the darkness. It's invisible, detectable only by how it bends light and pulls on nearby matter. This is a black hole, a place where gravity has become so strong that it tears holes in the fabric of spacetime itself. Imagine a star 20 times more massive than our Sun reaching the end of its life. For millions of years, the star has balanced two opposing forces, the nuclear fire in its core pushing outward, and its own immense gravity pulling inward. But when the nuclear fuel runs out, gravity wins completely and catastrophically. The star collapses in seconds. All of its mass compresses into a point smaller than a city, creating a gravitational field so intense that not even light can escape. Space and time warp around this collapsed star, creating a boundary called the event horizon, the point of no return. But the strangest thing about black holes isn't what happens to matter that falls into them. It's what happens to time. Picture an astronaut named David approaching a black hole in his spacecraft. He carries the same kind of atomic clock that ticks steadily on Earth, measuring seconds with perfect precision. As David gets closer to the black hole, something remarkable begins to happen to his experience of time. From David's perspective, time flows normally. His clock ticks steadily. His heartbeat maintains its regular rhythm. His thoughts move at their usual pace. But to someone watching from far away, let's call her Sarah, David's journey looks very different. As David approaches the event horizon, Sarah sees his clock begin to slow down. First slightly, then more dramatically. What feels like seconds to David stretch into minutes from Sarah's perspective. Then minutes stretch into hours. Then hours stretch into days. The closer David gets to the event horizon, the more extreme this time dilation becomes. Sarah watches through her telescope as David's movements become slower and slower, like a movie playing in extreme slow motion. His radio signals take longer and longer to reach her, and when they do arrive, they sound deeper and slower, stretched by the intense gravity. At the event horizon itself, something incredible happens. From Sarah's perspective, David appears to freeze completely. She sees him suspended at the boundary of the black hole, his image growing redder and dimmer as the gravity stretches his light to longer and longer wavelengths. To Sarah, David never actually crosses the event horizon. He remains frozen there forever, slowly fading from view. But from David's perspective, he passes through the event horizon in a normal amount of time. He doesn't feel frozen. He doesn't experience any dramatic slowdown. He simply continues falling, crossing the invisible boundary and plunging toward the black hole center. This creates one of the most beautiful and haunting paradoxes in all of physics. Two observers experience the same event in completely different ways. Both experiences are equally real and valid according to Einstein's theory of relativity. The event horizon itself is nothing more than a boundary in space-time. It's not made of any material. You can't touch it or see it directly. It's simply the distance from the black hole where gravity becomes so strong that escape becomes impossible. Light emitted from inside this boundary can never reach the outside universe. But the event horizon is special for another reason. It's where time dilation becomes infinite. At this boundary, time itself appears to stop when viewed from the outside. The event horizon is literally the edge of eternity. Think of space-time near a black hole like a waterfall. Far from the black hole, space-time flows gently, like a calm river. Closer to the black hole, space-time flows faster, like water approaching the edge of a cliff. At the event horizon, space-time plunges over the edge, flowing faster than light itself can swim upstream. This flowing space-time carries everything with it. Light, matter, time itself, all get swept along by the current. Inside the event horizon, space-time flows so fast toward the center that nothing can escape, no matter how fast it tries to move outward. The black hole's gravity doesn't just bend space. It bends time as well, stretching moments into eternities near the event horizon. This time stretching is so extreme that it creates a kind of temporal mirage. Observers far from the black hole see events near the event horizon playing out in slow motion, eventually freezing completely. Scientists have detected black holes throughout our galaxy by watching how they affect nearby stars and gas clouds. Matter falling into a black hole heats up and glows brilliantly before disappearing forever beyond the event horizon. These glowing disks of doomed matter are among the brightest objects in the universe. Some black holes are actively feeding, pulling in streams of gas and dust from nearby stars. As this material spirals inward, it forms an accretion disk that spins faster and faster, heating to millions of degrees and shining brighter than entire galaxies. Yet at the center of all this brilliant activity lies perfect darkness. The time dilation near black holes has practical consequences for space travel. If humans ever develop the technology to journey close to black holes, time differences would become extreme. A mission that takes a few hours for the travelers might correspond to years or decades for people back on Earth. This could theoretically allow for a form of time travel into the future. Astronauts could journey close to a black hole, experience time normally during their mission, then return to Earth to find that decades or centuries have passed. They would have traveled into Earth's future without aging significantly themselves. But the dangers would be immense. The tidal forces near black holes stretch objects along the direction of gravitational pull while compressing them from the sides. These forces become stronger as you get closer to the black hole, eventually becoming strong enough to tear apart any material object. Scientists call this process spaghettification because it stretches objects into long, thin shapes like noodles. Even the human body would be stretched beyond recognition by these tidal forces long before reaching the event horizon of most black holes. Yet black holes continue to fascinate scientists because they represent the most extreme environment in the universe. They're natural laboratories where space and time behave in ways that seem impossible according to everyday experience. The mathematics that describe black holes are the same equations that govern GPS satellites and time dilation on Earth. The principles are identical, just pushed to their absolute limits. Black holes show us what happens when Einstein's elegant equations are stretched to their breaking point. As you rest here in the gentle embrace of Earth's mild gravity, remember that the same forces that keep you comfortably in your bed also create these cosmic monsters where time itself can stretch toward infinity. Tonight, after this journey through the strange landscapes of space-time, you'll return to the familiar rhythm of your own time, flowing steadily forward like a quiet river carrying you toward sleep. Here you are, back where you started. Your heart beats steadily in your chest. Your breath flows in and out like gentle waves. The familiar darkness surrounds you, soft and welcoming. But something has changed during your journey through the mysteries of time. You carry new knowledge now, like a quiet light glowing somewhere deep inside your understanding. The clock on your nightstand ticks with the same steady rhythm it always has. But now you know that this rhythm isn't absolute. You understand that time is not the rigid ruler you once thought it was. Instead, it's something fluid, responsive, alive with possibilities you never imagined. As you settle deeper into your bed, feel the gentle pull of Earth's gravity holding you close. This same force that keeps you safe and comfortable also creates tiny differences in time's flow between your head and your feet. The effect is impossibly small, but it's real. Even lying still, you're experiencing the universe's hidden flexibility. Your feet rest slightly deeper in Earth's gravitational well than your head. Time flows just a whisper slower down there, pooling like honey in the valleys of curved space-time. Over your entire lifetime, your feet will age a few billionths of a second less than your head. It's a difference too small to feel, but large enough to remind you that time is not what it seems. Think about the GPS satellites circling silently overhead as you rest. Their atomic clocks tick faster than yours, compensating for their position in space-time. Every time you've used your phone to find directions, you've depended on Einstein's discoveries about time's flexibility. The universe's strange rules have been helping you navigate the world, invisible and elegant. Remember the astronauts you learned about, aging slightly differently as they orbit Earth at tremendous speeds. Their experience of time flows differently than yours, though both experiences are equally real and valid. There's no absolute timekeeper in the universe, no cosmic clock that defines the correct rate of time's passage. The twins Elena and Maya showed you how motion through space changes motion through time. Their love remained constant across the years that separated them, even as the universe wrote different amounts of time into their lives. Their story reminds you that time is deeply personal, shaped by the paths we choose through the cosmos. You've journeyed to the edge of black holes, where time stretches toward infinity. You've seen how gravity can bend not just space, but time itself, creating regions where moments expand into eternities. These cosmic extremes reveal time's ultimate flexibility, pushed to limits that challenge imagination. But now you're home, in the gentle rhythm of ordinary time. The same time that seemed so simple before your journey now reveals itself as something rich with hidden depths. Every second that passes carries the elegant mathematics of relativity. Every moment flows according to principles that seemed impossible just over a century ago. The light from your bedside lamp travels to your eyes at exactly 186,282 miles per second, the cosmic speed limit that connects space and time into a single fabric. This same speed governed the creation of every photon that has ever touched your skin, carrying energy from the sun, from distant stars, from the gentle glow of your room. As you breathe slowly and deeply, remember that you're moving through space-time at the speed of light. Not through space, you're lying perfectly still. But through time itself. Every second that passes represents light-speed motion through the temporal dimension of space-time. You're traveling through time as fast as anyone can travel when they're not moving through space. The universe has revealed some of its deepest secrets to you tonight. Time and space are woven together in ways that seemed impossible to imagine. Motion changes the flow of time. Gravity bends space-time itself. The past, present, and future might not be as separate as they appear. But these discoveries don't make the universe cold or mechanical. Instead, they reveal a cosmos that's far more beautiful and mysterious than anyone expected. The same equations that govern GPS satellites also govern the dance of planets around stars. The same principles that create time dilation in particle accelerators also shape the flow of moments in your daily life. Einstein's gentle revolution began with simple questions about light and motion. His curiosity opened doorways to understanding that we're still walking through today. Every time scientists detect gravitational waves from colliding black holes, or measure the expansion of the universe, or design more precise atomic clocks, they're building on the foundation he created by wondering what it would be like to ride alongside a beam of light. You've learned that the universe operates according to rules far stranger than common sense suggests. Yet you've also learned that these rules create the stable, predictable world where life can flourish. The flexibility of time allows for the precise choreography of orbital mechanics. The constancy of light speed enables the electromagnetic forces that power your body's chemistry. The same cosmic principles that create the most exotic phenomena in the universe also govern the gentle, familiar rhythms of your everyday existence. Your heartbeat marks time in a universe where time itself can stretch and compress. Your thoughts move through a brain that operates according to the same physical laws that govern neutron stars and black holes. As sleep approaches, you carry this new understanding with you into dreams. Time continues its steady flow around you, but now you know its secret nature. You understand that it's not just a backdrop against which events happen, but an active participant in the cosmic dance of existence. The darkness that surrounds you is the same darkness that fills the space between stars, where Einstein's discoveries reveal themselves most dramatically. But it's also the gentle darkness of rest, of peace, of the quiet moments when understanding settles into your mind like snow falling on a winter landscape. Tomorrow, when you wake, you'll return to time that feels perfectly normal and unchanging. But you'll carry with you the knowledge that this normalcy is itself miraculous, a stable island in an ocean of possibility where time can flow in ways that transform the very meaning of existence.